All right, so lesson 7.5, exploring the properties of exponential functions. We are now moving into graphing exponential functions. So, up until this point, we've seen quadratics, we've seen trigonometric functions. Now what we are doing is we are looking at exponential functions. And what is the main characteristic of an exponential versus everything else you've seen before is really this variable being in the exponent up top here, okay? So if you think about everything else we've done, right? Like we've had sine x, we've had x squared or y equals 3 times x squared or 3 times x. This is a linear equation. Really, the main difference now is that you have the variable being up top in the exponent, right? Like this is me saying 2 to the power of x. And what happens is as we start to put values in for this x, okay? So like any other function, you put values in for that x. You're going to evaluate this and it's going to give you values of y, or the value of your function, f of x. And how does that graph look? So what does it look like when we are taking 2 and putting it to the power of different values of x? Well, let's see, okay? So we are in this table right here, we are just filling in the table values. So this is f of x equals 2x. So when I calculate each one of these in this column, I'm evaluating 2 to the power of minus 4. So that is the same thing as me saying 1 over 2 to the 4 or 1 over 16, okay? So if we do that each time, all of these negative numbers are going to cause us to have a reciprocal, right? So 1 over 2 to the 3, right? Or I'll just write it out first, 2 to the minus 3, or 1 over 2 to the 3, or 1/8. This one is 2 to the minus 2, or 1 over 2 to the 2, or 1/4. This is 2 to the negative 1, or 1 over 2, which is 1/2. This is 2 to the 0. What is anything put to the 0? 1. This is 2 to the 1, so that's 2. This is 2 to the 2. This is 4. 2 to the 3, 8. And 2 to the 4, 16. Okay? So again, like every other problem we've done, you're just getting ordered pairs, right? Your table values gives you ordered pairs. So we're plotting the coordinate in this first one here, minus 4 and 1 over 16. Right here we're plotting minus 3, 1/8. Here we're plotting minus 2 and 1/4, minus 1, 1/2, 0 and 1, all right, like 0 and 1. Here we're plotting 1 and 2, 2 and 4, 3 and 8, and 4, 16. Okay, so literally just putting dots on the chart now. So negative 4 and 1 over 16. So that's really small, right? Like here's 1, so 1/16 would be like really close to that 0 line. 3 and 8, well, just still small, but slightly bigger, maybe there. 2 1/4, okay, so slightly bigger still, right there. Negative 1 and 1/2, well, it's halfway up, like there. 0 and 1, right here. 0 and 1. 1 and 2, right there. 2 and 4, right there. 3 and 8, right up here. And then 4 and 16, way up top here. Okay, so let's connect our dots now. So let's connect our dots. There we go. Okay, so now, like any other function, you need to include your arrows on both sides of this. So we have this going this direction, okay? I want to make a highlight of this point right here. notice how small these points are, okay? Look how small they are, right? Like they're the coordinates right here. They have the y values that are the fractions right here. Well, this arrow says, right, that as we start to go this direction, right, as our x values get really small in the negative, so like let's say negative 10, and as we go to negative, really large, like negative 1,000, well, mathematically, this is an x-coordinate, right? So you are technically saying, when we evaluate our function, f of x, you're saying, well, 2 to the negative 1,000, right? That's what you would do. Well, this would be 1 over 2 to the 1,000. What is 2 to the power of 1,000? That's like just some massive number, right? Like that's 1 over, I don't know, maybe like 2 with like 40 zeros behind it, like something crazy, right? Well, if you put that on your calculator, it's going to be something like 0.000000000, I don't know, 2, just for the sake of it, okay? Notice how it's not 0, but it's getting really, really close to 0. So we're still above 0. We're still positive. But like we're really, really close to 0. So this arrow is going to keep going this direction. All right? So I'm actually going to jump ahead here. Is there any x-intercept? So just using this, what I'm explaining here, right? And an x-intercept, that happens at some x value when your y is 0, right? So we have this curve going like that. Is there a value? Is there a value that you can plug in for this x, like this x right here? Can you take a value and plug it in there and get 0? Well, we just showed that if you take a really small number, something like 2 to the negative 1,000, you're not going to equal 0. It doesn't equal 0. It's something like 0.000002, right? Like just something really small, but it's still not 0. So if you think about a number line and, you have your axes like this, where this is y equals 0. You are still above this line. You're up here like this. You don't hit 0. Okay, well, that's on the extreme end of going in the negative x. What happens when you go in the really big positive direction? So like let's say what happens over here with these positive x values. Like if you go to positive 1,000. Well, notice your graph up top here. Look what happened as our x values started to get bigger. You started to get really, really large. Okay, because as you move this direction, you're going to be saying 2 to the power of, I don't know, like 1,000 again. That's going to be some massive number. Some massive number, right? So you're just going to keep getting larger and larger. Will this thing ever turn around and come back and intercept the x-axis? No, it won't. So is there an x-intercept? Explain why or why not? Well, no. There is no value of x that will make the function f of x equals 0. You will never have f of x equaling 0. That's what that means, okay? Okay, so I just wanted to explain that point while I was talking about this and why there's arrows on the graph. Let's go back up to C. What is the y-intercept? Well, y-intercept happens when you're 0 on your x and at some y value. Okay, so 0 on the x is right here, so it's right here. Well, what coordinate is that? Where are you 0 on your x? Right here. This is your y-intercept. So your y-intercept is at the coordinate 0, 1. All right, well, state the domain and range. Domain is talking about your x values as it has been for every other function. So ask yourself, is there a value of x that you cannot input? Meaning, if you were to fill out this table of table values here, is there a really large x value that you would not be able to use? Like, is there something where you put like 2 to some large number, like 3,000 or something? Is that not possible? And vice versa. Is there a really small number that you're not allowed to use? Is there something like negative 5,000? Like, are you not able to put that in your calculator? So when you think about saying what is your domain of range, is there a value of x that you can't beat? Well, no. This is a fundamental characteristic of an exponential function. X belong to real numbers. There is no restrictions on your x. Now on your y's, so we talk about range. Y belong to real numbers. Now, there is a restriction on your y, and we just talked about it right here. We literally said the function can never equal 0. So, meaning this function will never go down here. It will never be below 0. There is no value of x that will cause your function to turn negative. So your y's always have to be bigger than 0. And notice that I did not put an equal sign here. Okay? It's just bigger than 0. So there's this new word that we use, okay? It's called an asymptote. And what an asymptote means, it's a line, like kind of like your, like, you know how your axes of symmetries are lines, but like they don't actually exist. An asymptote is a line that you cannot cross, okay? A line you cannot cross. So in this thing right here, in this graph, we cannot cross this line right here, this black line, right? Because if we cross that, that means we are in the negative space. That means at one point in time, your function right here would have to equal 0. But it can't. We've shown that you can't ever be 0. So what there is there's this line, this hidden line right here, this dashed line that we say y is equal to 0, and this is your asymptote, okay? It's a line that you cannot cross. You can never cross y equals 0. So the equation, that's why we write it as y equals, and then you state the value that you cannot equal. All right, so y equals 0. This is the equation of your horizontal asymptote. Horizontal, because notice, it's a flat line like this, okay? So horizontal asymptote. State the intervals of increase and decrease. So what these words mean? Well, increasing says that if you read a chart left to right, okay, so if you start over here in your negative x's and you read it, like so you're reading this direction, and you go all the way to your positive x's, are your y values getting larger? So if you read left to right, actually, you know what, let me put it over here. I'll just give a summary. Increase. If left to right, y values are larger, then you're increasing, okay? And vice versa, you are decreasing. You are decreasing if, once again, you read left to right. You're always reading left to right. The y values are smaller. So let's look at our graph. If I go up here, if I read my graph left to right like this, okay? So that means if I take any point and I go to the right of it, did I go up or did I go down? Well, in this case right here, I went up. And same thing, I go left to right, I went up. So this graph is increasing. Notice that wherever point, if you take any point that we've graphed so far and you look to the right of it, it is always greater than what you started with. So this going from here, this point to this point, you went up. So you increased there. You went from here to here, you went up. So you actually increased there too. So this graph is always increasing. So when it says intervals, it means it's saying, tell me the x values that you're increasing across. Well, in this case, I'm increasing across every single x. So my interval, in this case, is actually negative infinity, all right, negative infinity to positive infinity, all right? This means you will be increasing across every single x value. You will never decrease. So increasing, and this is your interval. That's your interval, negative infinity to positive infinity. So let's do example 2. Complete the table of values for the exponential function f of x equals 1/2 to the x. Very similar to the previous problem. The only difference is here we have a fractional base. We have a base value that is technically bigger than 0, but less than 1, okay? And if we contrast to what we did above, here we had a base value bigger than 2. Or sorry, bigger than 1. I read 2. But base value bigger than 1. And now this will be important in a second, okay? So here, we're graphing 1/2 x. Well, like all things with math and table values, you are essentially evaluating f, which is 1/2 to the x. You are taking these x values and substituting them in for that x right there. So you're saying, okay, well, what is 1/2 put to the power of 1/4? Just like you did before, well, you deal with the negative exponent, so that tells you to flip your inside bracket. So now this is actually 2/1, but 2/1 is what? That's just 2. And then you put that now to the positive exponent, 4. And 2 to the 4 is 16, okay? So every time you deal with this negative exponent, really you're just making your base 2. You're doing the opposite, right? So this again would be 2 to the minus 3. Well, that's going, 1/2 to the minus 3. That's going to be 2/1 to the 3, which is just 8. This is going to be negative 2, 1/2 to the negative 2, because your function is still 1/2 as a base. You are flipping your base to deal with the negative exponent, so 2/1 to the 2, which is 4. This is 1/2 to the negative 1. Again, flip your fraction, so it's 2/1, right? 2 divided by 1 is just 2, so it's 2 to the 1, or 2, right? So then 1/2 to the 0. Well, anything put to the power of 0 is just 1. All right, next one. 1/2 to the 1. Well, anything to the power of 1 is just itself, so that's just 1/2. 1/2 to the 2. Well, that's like me saying take 1/2 and multiply it by 1/2, right? You're writing it twice. You're doing the multiplication twice. So that's 1/4. 1/2 to the power of 3. Well, again, you can also just use your exponent laws, which we've done so much of now. Take that 3, distribute it. So that's 1 over 2 to the 3, or 1/8. Do it again here. This would be like 1 over 2 to the 4, or 1/16. So, what you've just done again is you've created a set of ordered pairs. We are plotting the point -4 in this case and 16. -4 and 16. So I'll do it this time by where I just write each coordinate by looking at table values, and I'll plot it first. So -4, 16, we're up here. Then we're plotting -3 and 8. Okay, so -3, 8, right here. Then we plot -2 and 4, -2 and 4 right there. -1 and 2, so -1, 2. Here you're plotting 0 and 1, 0 and 1. Here we're plotting 1 and 1/2, so 1 and 1/2, so we're about halfway there. Here it's 2 and 1/4, so we're getting small again, very small, so 2 and 1/4, like there maybe. Here it's 3 and 1/8. Okay, so 1/8 is here. And then 4 and 1/16. Really, it's hard to distinguish between the 16th and the quarter, so like right there. So if we connect our dots, we go. Oh, that's a horrible me connecting my dots. There we go. There we go. And just like always, I can still put values like 6. I'd be able to compute that. I'd be able to compute 7. So that means this arrow is going to keep going like this. Like that. And same thing. I'd be able to keep going values of like -5. I can go -6, right? So this graph would just keep going up like that. So let's go through and complete the rest of the question. What is the y-intercept? Once again, you're looking for the x-coordinate that gives a y, sorry, other way around. You're at 0 on the x, and you're at some y value, right? That's what the y-intercept is. Your x is always equal to 0. So where is x 0? Right here. So that's your y-intercept. That's the y-intercept right there. That coordinate is at 0, 1. Is there an x-intercept? Well, look. Is there a value that will make this function equal to 0? Because again, what is an x-intercept? An x-intercept is at some x-coordinate that would make your y, your function, equal to 0. And no, look, there is no point. As your numbers get really big, right, as your numbers get bigger in the x, so here you can see that our x's are increasing, and look what happens. You're just getting really, really small. Your y's are getting smaller and smaller. 1/8 is smaller, or sorry, bigger than 1/16. But there is no point. 1/2, if you put it to the power of a really large number, like 1,000, it is still bigger than 0. Yes, it's really small. Yes, it's something like 0.000004, but it's still bigger than 0. So just like in your previous problem, there is no x-intercept. No x-intercept. All right? And y, again, there's no value for x that would make f of x, which is equal to 1/2 to the x, equal to 0. State the domain and range. So, is there value for x when we state the domain that you can't be? Well, let's look at this. This arrow tells me that I'm going to keep going in this direction all the way to technically -infinity on my x. And then this arrow right here tells me I'm going to keep going this direction. So again, no, there is no restriction on your x. That is a fundamental to an exponential function. And then range. Same thing as above. Range, y's have to be bigger than 0. Not bigger and equal, bigger. Okay? What is the equation of the horizontal asymptote? So again, you have this hidden line here that you cannot cross. And that hidden line is at y equals 0 because you can never have a y coordinate that is 0. So the equation of the horizontal asymptote is y equal to 0. State the intervals of increase and decrease. Well, let's look. When I read left to right, so if I start at this point right here, if I go to my next point over, which would be right down here, I had to go down. Same thing here. If I went over, I had to go down. So that pattern is consistent across the entire graph. So you are decreasing across negative infinity to positive infinity. Because this is you reading from left, which is the negative infinity is the most left you can get, all the way to right, okay? So don't write this. You don't have to write this. This is just me explaining it to you, okay? This is what you would say. That's what you say. So in general, functions of the form y equals d to the x are called exponential functions because the variable x is in the exponent as I kind of introduced this lesson to you, okay? So these are the properties of the exponential function. The base must be positive, right? What that means is that you cannot have this. Negative 2 to the x. That's just a fundamental property, right? The y-intercept is always 1. Look, we did 2 examples where we changed the base, and it was always at 0, 1. And it didn't matter. We changed the base, and we still had no x-intercept. There is a horizontal asymptote, which we call HA, at y equals 0. The x-axis, y equals 0, is this horizontal asymptote. That's this right here. Domain belongs to your real number. Range is being bigger than your horizontal. This is your HA. Okay? And then if d is bigger than 1, so in our first example, this was example 1, example number 1, you're always increasing. When d is less than 1, and really actually this should read right here, 0, d, 1, and sorry, let's fix our note back up here because I wrote b, I should have wrote d. Again, they change the letters sometimes, so I guess d. Okay, so if d, 0d is less than 1, well then y equals d to the x. Right? This should be increasing, right? This is like example 1. And this is like example 2. Number 1. And again, this should read right here, 0d1. Okay? So that is our intro to exponential functions. And there is our homework. Bye for now.